Welcome back. We're going to continue looking at shear moment diagram problems. Now we're going to revisit this problem that we worked earlier where we just simply found the shear, the normal, and the moment at 3 different points. Here we're just going to worry about the shear and the moment, but we're going to go ahead and draw shear moment diagrams on this one. So we're basically going to rework that problem. And again, I like to just kind of keep these guys nice and lined up. I'm going to go ahead and make sure I've got enough room to draw that rectangular load right on top there. It's going to span a total of, what do we got there, 4 meters. So we're going to draw a 12-meter long beam, obviously to scale or scale down. I don't know if I'd say it's to scale, but hopefully you get the idea. So break it up into thirds, 1/3 without a distributed load, 1/3 with, one more third without. We've got a pin here at this point on A, and again a roller on a horizontal surface at, we got A and B. This distributed load is 500 newtons per meter. A keen eye will notice the similarities to the previous problem that we just worked in the last end of lecture 17. Hazel is talking to, my puppy Hazel is talking to our new kitten that was the universe decided to bestow upon us this week. Hopefully they're not too loud, either of them. We'll see how they do. So, again, we've worked this problem previously. We worked a kind of a different version of this and just drew shear moment diagrams for where we had a single force, very similar setup. But here we're going to draw shear and moment diagrams for this problem. Okay, now when we talked in the last lecture, lecture 17, page 5 of 7 for me, procedure: find the reactions if you possibly can. Then determine the number of cuts needed. Where do cuts occur? Cuts are going to occur wherever the external load changes or we have external load applied. Specifically if you have a change in the distributed load, which we do have a distributed load that's going to change a couple places. So we're going to determine the number of cuts needed, and then we're going to use equilibrium to find the shear as a function of x and moment as a function of x for each one of those cuts. And then finally we're going to draw graphs where we label the max and min moments. And notice that you can see mathematically, they talk about it in the text, we can show that in these expressions here, that the shear is going to be the derivative of moment, and the distributed load is going to be the derivative of shear. So with that in mind, again, we've worked this problem previously, and step 1 of our process there says find reactions if possible. Well, we can find the reactions here. We've already found them previously. If you go back to page, looks like it's page 3 of my notes on the previous lecture, we found that AY is going to be 1,000 newtons and B is going to be 1,000 newtons. And there's no x direction forces here, so AX is going to equal 0. If you need help finding those, we really need to review material from 2 exams ago at this point. You really need to be able to find reactions for these at this point. So we found the reactions, did that in a previous problem, so we're going to carry them over. Now we need to determine the number of cuts. So I have a distributed load here, but I have no distributed load here. I have no distributed load there. So the distributed load goes from 0 to a constant 500 newtons per meter. And then again, at the end of this, it's going to change again back to 0. So I need to know, basically, that the shear and the moment, as functions of x, are going to change in this region between 0 and 4 meters. And then when this, from here, right at 4 meters, you now have a distributed load, so that's a change. So we need a cut right in here from 4 to 8 meters. And then after that, we go from 500 newtons per meter down to 0. That's another change. So I need a cut in here from 4 I'm sorry, from 8 to 12 meters out here. So I'm going to need, if I look at the number of cuts, there's going to be 3. 1, 2, 3. 3 cuts needed for this. Okay, so we're going to do 3 cuts. We're going to start with the first one. Somewhere in the range of 0 to, basically x is going to be between 0 and 4 meters. Looks like my camera cut out there for just a second. I think it's back though. Let's see how it's going. I can apply my reaction force here at A of 1,000 newtons. I've got a shear that I've now exposed, and I've got a bending moment. You could draw a normal there, but there's no x direction forces, so the normal is going to be 0. And that cut is going to occur at some arbitrary distance x. So if I take sum of forces in the y direction, set that equal to 0, I've got 1,000 newtons going up, and then going down, I've got my shear force. That, again, sums to be 0, so my shear through this region is going to equal 1,000 newtons. Again, we've done this problem before where I've made these 3 cuts. Now we're going to write these as functions of an arbitrary x value. So the shear stays a constant value through here, but the moment, if I take my sum of moments about any point, I'm just going to take them about A to keep it simple. If I take my sum of moments through here, I've got a positive bending moment, and then causing a clockwise or negative moment, I have the shear force applied at a distance x. Well, I have my shear is 1,000 newtons, so I can plug that in. So this is easy to solve. Solve that. My moment is going to equal whatever my shear is. Well, my shear is going to be a positive 1,000 newtons times whatever value x is. So that's a linear equation. Now, a good habit would be whenever you've got an expression right here. Now, this one's constant. You wouldn't have to find the limits on this, but it's a good idea to go ahead and find what are your limits if you find the moment at x is equal to 0. Well, you plug in 0 here, and you would get 0 moments. And what would I find if I plug in, because we're going to have to draw graphs of these, so knowing the endpoints from 0 to 4 is probably going to be helpful. So it's a linear equation going from x is equal to 0 out to x is equal to 4. So one endpoint is 0, 0. The other endpoint is going to be where x is equal to 4 if I plug in 4, and we should say 4 meters. If I plug in 4 meters here, this is going to be 4,000 newton meters. So I'm going to have a line with endpoints 0, 0, and 4,000. And that's going to make graphing that pretty easy when you do that. You don't necessarily have to do that, but I've learned over the years this is a good habit. When you get an expression, go ahead and find the endpoints, and that'll make drawing your graphs easier. Okay. Come here, kid. Everybody. Will you show off for them? This is Lucy. Come here, Lucy. Come here. Come here. Don't bite the light. Don't get the light. Come here. Will you get under the camera for them? Will you come show them? Hey, come here. Come here. I don't want to have to change my camera angle. You kind of get to see Lucy there a little bit. All right, come on, Lucy. We got work to do. We got work to do. All right. I'll post a picture. Pause and take a picture of her here in a second. Let's just do that. Let's get to that out of the way. Hey, look. You look at the camera. Everybody, this is Lucy. Lucy, we got to get to work. That's Lucy. She found us this week. She showed up at our front porch under our cars. The universe decided we needed another cat in the house. So here we are. Okay, Lucy promised she's going to let us get back to work. I'll believe it when I see it. Here we go. All right, so we've taken, what are we trying to do? We're trying to find shear and moment diagrams for this thing. We've made a cut here. We made a cut here. Wish you could see how cute this is. We've made a cut here. We've made another cut there. All right. We've found now equations for shear and moment for the first cut from 0 to 4 meters. All right. Now, let's do the next cut. Now, again, I like to try to line these up. So I'm going to kind of come straight down through here, and we're going to cut somewhere in the middle there. Now, it doesn't have to be perfect, but it's a good practice. And when you actually go to draw your shear moment diagrams, if everything's kind of lined up, I find it helps me. If it doesn't help you, then you can just ignore that, and that's okay. So we're going to draw a cut in here somewhere. This is going to be for 0. I'm sorry, not for 0. This is going to be from 4 meters to 8 meters. In this range, now we've exposed shear and moment when we cut through here. Still have this force at point A is 1,000 newtons. And we do have, my preference is to leave a distributed load distributed when I cut through it. So I've cut through this distributed load, and it has, again, an intensity here of 500 newtons per meter. Now, it starts at a distance of 4 meters, and the total distance out here to where that occurs is going to be x. Now, a bit of a challenge is we're going to have to find where this center is located. So if we need to find where the center of that is located, I need to know what this span is. Well, if this is x and this is 4 meters, then this span right here is going to be what? This is going to be, the total is x, and it's 4 meters less than x. So it's 4 meters less than x to get in there. And so this guy's going to be right in the center of that. So it's going to be half of this length plus this length. That's going to get me to the center from point A, if I take my sum moments about point A. You could also call this like point C and take your sum moments about point C, and then this maybe is a little bit easier to find. But anyway, I think we can build it. Let's go ahead and find shear first. So we can find shear. Well, let's do this. Let's do the standard operation. Sum of forces in the y direction equals 0. What do I have in the y direction? Well, I have 1,000 newtons over there at point A, minus the shear force, and then I have this distributed load. Well, I'm going to condense this down to a single force, so it's negative 500 newtons per meter. It is applied over a distance, so its width is x minus 4 meters. And that would give me the area of this rectangle. This is the height, this is the width. So this would give me how much of that force we've already experienced. So I'm going to apply, I need to multiply this through, distribute that through. So we're going to say the shear, which is what I'm looking for, is 1,000 newtons minus, it's going to be 500 times x, so 500 newtons per meter times x, and then minus 500 newtons per meter times 4 meters. So this is going to be minus 500 times a negative 4. It's going to be plus 2,000. I've got newtons per meter times meter. That's newtons, 2,000 newtons. So I've got a couple of constants here, and I've got a linear expression term there. So my shear is going to simplify down to 3,000, a positive 3,000 newtons minus 500 newtons per meter times x. This equation is going to be valid for this range from 4 meters to 8 meters. So what you might do is you might find the endpoints and say, well, what happens if I plug in 4 into this equation? So if I plug in 4 meters in here for x, all right, well that's this is a negative 500 times 4 meters. That's going to give me a negative 2,000 newtons. So I'm going to have positive 3,000 minus 2,000 newtons at this point. So it's going to be 1,000 newtons Interestingly, that's the same value here. Okay, there's some reasons that makes sense we can talk about. If I calculate this shear at an x value of 8, so if I plug in 8 in here, this is 500 times 8 gives me 4,000. So 3,000 minus 4,000 is going to be minus 1,000 newtons. So those are the endpoints. I've got a linear equation. Right, the y-intercept basically is 3,000, a negative slope of 500 newtons per meter, and I've got endpoints. At 4, it's going to be a positive 1,000. At 8, it's going to be negative 1,000. Okay. So far, so good. That's a bit abstract, but we're getting somewhere. Let's find our moments. I got to find my moment equation. So sum of moments, I'm just going to take it about point A. That's going to add up to be 0. I'm going to add my bending moment. It's positive. I've got my shear force out here, so it's causing a clockwise moment. So minus whatever my shear force is times this distance x to get out to the shear force. And also causing a negative rotation is going to be this distributed load. So it's going to be causing a clockwise rotation. So the force is going to be 500 newtons per meter. It's applied over a distance of x minus 4 meters. That's the force. This is the force. This is force per distance times distance. This gives me the force. And I need to find where it's located. Where it's located, it's going to be half of this little distance here. It's going to be right here in the middle. So it's going to be x minus 4 over 2 plus this 4 meters. So it's going to be x minus 4 meters over 2 plus the 4 meters. Okay. Remember, moments are going to be force times distance, or lever arm, or moment arm if you prefer. All right, it's just algebra. I know it looks weird because we got units and stuff in there, but it's just algebra. All right, so let's do this. Let's say let's add both these to the other side of the equation. So my moment is going to equal shear times x. I'm going to go ahead and distribute this through. So I'm going to have a polynomial here, and it is what it is. So plus.
Sorry.
It's okay. Plus, let's see. I'm going to pause it here and make sure I do this right. All right, that's not the kind of thing I wanted to work out live. I haven't worked this problem before. A lot of these problems I've worked before, that one I haven't. So this is what I did. I took this quantity here, right? This one times this one, and I FOILed it out. I didn't want to write all the terms, so I just said, you know what, let A equal X. B is the 4 meters because it shows up here and here. It's negative here, positive there. C is going to be this x minus 4 meters over 2. And I'm just going to FOIL this guy out. You FOIL this out, you get AC plus AB minus BC minus BC minus B squared. I'm going to go through this very quickly, pause this and look at it and kind of scrub it a little bit and make sure it makes sense to you. But it's if you take, again, A being x, you take A times C, that's this guy, and that simplifies to x squared over 2, right? And then, so that's x times this x, and then x times this minus 4m, so this is minus 4xm over 2. I've got this 4xm, that is A times B, that's going to come straight down here. I've got minus B times C. This one's a bit complicated. B is minus 4 meters, and C is this guy. So this 4 meters times x over 2, that's this guy here. I've got minus 4 meters times a minus 4 meters over 2. So minus 4 times minus 4 gives me positive 16 meters squared over 2. And then I've got b minus b squared, comes out of the FOIL, right? Minus b times plus b, minus b squared. So that's minus 16 meters squared. And that carries down here. And you can see what happens from there. This guy stays by himself. He's the only second order term. I've got 3 linear terms here, combine them, these two add up, I've got 2 times this over 2, and this is minus 4xm plus 4xm, they go away. Here I've got 16 halves of a square meter, and here I've got a negative 16, so this ends up, this is really just positive 8 minus 16, this just ends up minus 16 meters. So that's what we end up with, that whole thing. Again, pause back up there and go back through that if that doesn't make sense. So I've added this term over here. Again, I've found this term already. So it's 500 times this, the result of this term. So it's 500 times x squared over 2, and then minus 500 times 8 meters squared. It's 500 newtons. This has got a term of newtons. It's like, wait, where's it at? This has got a term of newtons per meter. I was like, wait, the unit's got to work out. The newtons per meter carries through, so 500 newtons per meter times x squared over 2 minus, then again, the other one is 8 meters squared, so minus 500 newtons per meter times 8 meters squared. Okay. More than I would ever ask you to do on the exam. Although you can technically do this one without doing the algebra. That's another discussion. We call it by inspection. That's another discussion for another time. This video is going to be long, by the way. All right, what did we do? We found shear force in this range, because I need to take shear times x to find the moment caused by this shear. Well, the shear we found in this range to be this expression here. Newton. It's Newton meters, right? No, it's just Newton. I don't know why I've got 2 newtons there. 3,000 newtons minus 500 newtons per meter times x, and that gets multiplied by another x. So I've got the shear is going to be 3,000 newtons times x minus 500 Newton per meter x, and that gets multiplied by another x. So this actually ends up being x squared, minus 500 x squared. And then I've got these two terms that I need to add to it. Right? So this is this. I need to add these two terms. So plus, skip as much as of the algebra as you're comfortable skipping. 500 Newton per meter x squared, this term, minus, I've got 500 times 8, that's going to be 4,000, so minus 4,000. I've got newtons per meter times meter squared, that's going to be Newton meters. I'm going to pause there. Okay, I paused there because I'm like, that doesn't look right, Steve. There's a half right here. So don't forget to carry the half. I forgot to carry the half. You could go ahead and write this as 250 if you like. That's okay, because I am going to simplify this in the next step. So let's see here. I've got a constant term, no x on this one. I've got a linear term, 1x, and I've got 2 second order terms here. So this is going to be a polynomial equation. If you ever talk to a high schooler, it's like, why do I ever need to learn polynomials? Nobody ever uses these. You can tell them that they don't know anything about life and they need to pay attention in school. Minus 500 newtons per meter x squared plus 500 divided by 2 newton per meter x squared. So you end up with minus 250, because this is a positive 250 minus 500, so it's minus 250 newton per meter times x squared. That's these two terms combined. Plus 3,000 newtons times x minus a constant 4,000 Newton meters. So a second order polynomial. Okay. As we've done up here, you might go ahead and plug in. To keep this video from getting too long, I'm going to suggest you calculate, get ready to pause here and calculate on your own time, where we plug in 4 in for x, 4 meters in for x here, and calculate that value, and then also come over here and do find m at 8 meters, plug 8 meters in for x, and find that value. I'm going to pause and calculate those to keep this video somewhat. Okay, there's my math. Double check it against yours. They both come out to be 4,000, positive 4,000 Newton meters at both points here. That's kind of interesting. Why, Steve, how does that work? Well, look at it. This is a negative concavity. I'm hoping you guys have had calculus where you've looked at concavity and stuff like that. If not, I'm really not sure you're in the right place. But if you take your second derivative here, you get a negative term, right? So it's negative concavity, concave down. It's a parabola. So most likely you just have a maximum somewhere in between these 2 points. You're going kind of, you got this U shape, and these are the 2 endpoints on that U shape. So it just goes up and comes back down to the same value. Okay, Steve, what the heck are we trying to do? Well, we wrote that down at the very beginning. We're trying to find shear and moment diagrams. We found our reactions. We figured out that I needed 3 cuts. I've already made 2. This one was kind of a challenge. That's okay. So I've made 2 cuts. This one's a bit of a challenge. Let's look at this third cut. I've got to make a third cut now. I need to write equations. I now have equations for shear and moment here, and endpoints for the one that's variable. I've got now an equation for shear with endpoints, an equation for moments with endpoints for the second cut. Let's do now the third cut. This is lecture 18, page 2 of something. We'll figure out how many pages in a second. All right, so that third cut, I'm kind of trying to line it up with my original diagram up there. Again, I've got a force here at A of 1,000 newtons. In what you can do, if you're cutting, at this point I'm cutting after the end of the distributed load. I'm cutting in here somewhere. So you can go ahead and convert this now. I don't like, when I cut inside a distributed load, I like to leave it distributed. That way I can see what's actually going on. But once I'm outside of it, you can convert this to a single force. That's 500 newtons per meter over 4 meters. So it ends up a single 2,000 Newton force at a distance of 6 meters from that endpoint. So that is 2,000 newtons at a distance of 6 meters. Again, we've cut at this point and exposed a shear and bending moment at some arbitrary distance x. Okay, I'm going to pause it here to keep this video short. I would suggest you do the same, and let's write equations for shear and moment now. So go ahead and pause. Okay, this is what I've got. Negative constant 1,000 newtons. I get my moment equation should be a positive 12,000 Newton meters minus 1,000 newtons times x. And remember, this is for x between values of 8 meters and 12 meters. That's our range for these equations. So go ahead and find where I plug in x is equal to 8 meters here, and where I plug in 12 meters for x. Go ahead and find those values. Pause it, get those values, and let's come back. All right, looky there. We start at, hang on a second. So, we start at 4,000 Newton meters, and when you plug in 12 meters at the very end of the beam, notice it goes back to 0. Sometimes that's a good thing, especially if there's no other couple moments on the board to take it back to 0. Now, I'm going to do something additional here. I'm going to redraw my initial diagram before I draw my shear moment diagrams. Right. I'm going to draw it kind of thin and simple. I've got 1,000 newtons here. I've got 1,000 newtons over there. And I've got, right in the middle here, I've got this distributed load. 500 Newton per meter. Now remember last time we said that the distributed load is that the derivative of the distributed load gives us the shear, and the derivative of the shear gives us the moment. You can kind of see that when this plays out here. Okay. Or is it different? Yeah, I said that wrong, didn't I? Looking back at my notes. I always get those mixed up. The distributed load is the derivative of the shear. The shear is the derivative of the moment. Okay. So what does that mean for us? Well, if you go back and look at your equations for the shear, let's draw the shear first. Remember, on our first cut, our shear stays a constant 1,000 newtons. In our second cut, it's a linear expression going, you've got this linear expression here, negative slope, and it starts at a positive 1,000 newtons at x is equal to 4, and it goes down to a negative 1,000 newtons at the end of this range at x is equal to 8. And if you look at your third cut, which we just did, notice the shear is a constant negative 1,000 newtons from 8 to 12. So that looks like this. If I draw my shear, it's going to go, on the y-axis, I'm going to go from a positive 1,000 newtons. Draw my x-axis even with my beam out here. No, I'm sorry, this is x. This is my x-axis, and this is my shear as a function of x. And then notice down here, or I'm sorry, I've got my other limit down here, is 1,000 newtons on the negative side. So remember, we started at a constant 1,000. It does that for the first 4 meters, stays constant. And then it turns into a linear expression. All right, it's a linear expression that goes from 4 meters out to 8 meters. It starts at 1,000 newtons, and at 8 meters it goes down to a negative 1,000 newtons. And then from 8 meters on out to 12 meters, it stays constant. And what you find is if you line these up perfectly, notice that I've got right here a force that's going to push this up to a positive 1,000 newtons. It stays like this. Then I hit an area in here where it goes down. It's going to cross the x-axis in here somewhere. And then it's going to go out here, and I'm going to hit another positive 1,000 Newton force at the other reaction. It's going to push us back up to 0. So after it's all said and done, sum of forces should be 0. I should come back to 0 at the end. So that's my shear graph. Now let's look at my moment graph. So if I go back and look at my expressions for moments, initially I've got a simple equation, 1,000 newtons times the x value. So at x is equal to 0, we start at 0, we go up to 4,000. Okay. The second one, we had this crazy algebra we had to do. It's really not that crazy, it's just algebra 2 for high schoolers, but it's probably been a while since we really had to do anything that intense, and maybe never, especially not with units. I get that. This was not easy. It wasn't too hard, but it wasn't easy either. This is our expression. Second order polynomial, negative concavity, endpoints, positive 4,000 Newton meters at both x is equal to 4 and x is equal to 8. And then if you look at your third equation, he's right here. 12,000 minus 1,000x. And you start at positive 4,000, go down to 0. So we are going to go on our moment diagram. We're going to go from 0. It does not appear to ever go negative. This is my moment as a function of x. It's going to go up to 4,000, and then it is going to increase just a little bit beyond that. Remember that is 1,000 times x for the first 4 meters. So it's just a linear expression up to this 4,000 Newton meters here. And then I've got a concave down expression that has an endpoint over here, also a positive 4,000 Newton meters at x is equal to 8. So I just need a concave down shape there. You can plot some additional points. In fact, we need to find this point, which is going to line up right there. Notice I've crossed the 0. I have a 0 point in my derivative. That's going to tell me what this local max value, or the x value, where that local max is going to occur. It might occur right there at 6. I don't know. We'll see. And then I've got a linear expression out here with a negative slope that has endpoints of 4,000 and then at x equal to 12 all the way out to 0. So this is my curve here. We normally shade under the area, or shade the area of the curve. We do need to find this guy. Where does this guy occur? Well, remember my equation through here. For my shear, my equation through here is 3,000 minus x. I need to find where this equation, where does that equal 0? Shear of x, we said that is 3,000 minus 500x. We want to know where does that equal 0. No. You can solve that and you'll find x is equal to 6 meters. That's where your 0 is going to occur. So this is going to occur right at 6 meters. You can find that through algebra. And that's going to tell me the location of this max. So I need to find the equation for that max guy. That's this crazy second order polynomial equation. So I need to run m is equal to 6 through that expression. My max moment is going to occur where x is equal to 6 meters for that expression. Right. I'm going to pause it and do the math so this doesn't get too long. Okay, I cheated. I look back here. Remember, we did this problem earlier where we cut it at 6 meters. We found the bending moment at this, we call this point D. The bending moment at point D was 5,000 Newton meters. So if we run that, this is the equation. We found the equation. If this is x, we found the equation for this moment. But earlier in the previous problem, we had actually found this value at 6 meters. We found it to be 5,000 Newton meters. So you can do the math. You can run that through your calculator, but we've already done that. So there we are. This is my maximum moment, 5,000 Newton meters at x equals 6 meters. Now, real quickly here, I'm going to try to get quite a bit of that on. I'm going to get most of that on the page. Notice you can apply calculus principles and solve this problem. As we've already said, the shear is the the shear and the distributed load are all related through calculus. We said the distributed load is the derivative of the shear. We said the shear is the derivative of the moment. So notice through here, my moment equation, this is a second order polynomial. The derivative of that is, and this is concave down, so the derivative of that is a line with a negative slope. Right? The shear, the derivative of the moment. The distributed load is the derivative of the shear. Here I've got a negative sloping line. The derivative of a negative sloping line would be a negative constant value. Right? If memory serves, this line, the equation for this line here, I'm getting my notes all mixed up. If memory serves, the equation for this line here has a slope of minus 500, the same as the value of this distributed load. Right? So, calculus can do this. You can actually do this by what's called inspection, where you don't actually have to do any equations. We might do that on another problem, but this is plenty of length for this particular video. If you've made it this far, great job. You toughed it out. We'll go from there.